All right, that should be underway. Terrific. So today we're going to be introduced to computed tomography, basically what the images look like, how the image data is collected by the hardware, and how the technology has evolved over the last 30 to 40 years or so. Because it started out as a very simple and slow process in terms of the data collection, and now it's quite a sophisticated and very fast process. So I'm going to use figures from Bushberg, and I think all the other figures should be annotated as to their source. So this is what a modern CT scanner looks like. It is essentially a cylinder, right, with a hole cut out of the middle, so it looks like a donut. And this hole is about anywhere from 75 to 100 centimeters in diameter. So it's actually has a fairly large opening. It's not a claustrophobic experience going into a CT scanner because it's pretty short. It's about 80 centimeters long. And so unless you're having your head scanned, your head is usually outside of the scanner when your pelvis or your heart or something else is being scanned. This patient on the patient table is having ECG leads applied to the chest so that with this monitor you can watch their heart rate and look at their EKG. The table upon which the patient is lying is essentially X-ray translucent. It doesn't stop many X-rays. You can see it in images, but it doesn't attenuate many X-rays, so you can just shoot X-rays right through the patient. The other thing to notice is this device, which is a power injector. And so this is, instead of injecting a contrast agent into the patient's vein with your hand and a syringe, this is an automated way to do that so that you inject at a very regular rate and you can inject a very specific amount of contrast agent into their veins. The contrast agent stops X-rays very well, and so it shows up as a very bright source in the image if you want to look at vessels and things like that. So once the patient is set up, a laser is used to align the system to the patient's physiology or morphology, and then the patient is essentially pushed into the scanner and you start your acquisition. So what's all the excitement about? Here's an example CT image of somebody's head. And let's look at this one on your right. As you can see, the components of the brain are generating different contrast or different intensities. So these are white matter tracks, this dark stuff, and this stuff here are gray matter in the cortex. This very bright signal here is the bone of the skull, and bone stops X-rays very well, so it shows up very bright on these scans. The dark signal back here is cerebral spinal fluid. It's like water, pure water, and then there's air on the outside, which gives a very low signal. So the brightness in a CT image is actually proportional to the stopping power or the amount of X-rays that are stopped by that tissue. So if it stops a lot of X-rays, it gets bright. If it's air and it doesn't stop X-rays, it looks dark, right, in the background. That's opposite from, say, a shadowgram, right, where you're basically projecting X-rays through somebody and you look at a screen and you measure the shadow of the X-ray beam. So here's an example of three-dimensional data taken in a patient's brain after the injection of a contrast agent. And so you can see that there's very bright signal in the vessels in the brain. So these are the vertebral arteries coming up here, and very small vessels are well visualized when that contrast agent is in the brain. And so if you want to find something like an aneurysm, this is a very sensitive way to do so. You would like high resolution to make this picture, right? You want to see very small vessels. And so all of the arguments that Dr. Liu has been making about making systems with broad modulation transfer function, i.e. high resolution, apply here. You would like a lot of spatial frequencies submitted through the system so that you can resolve small objects. In this case, we also are looking at three-dimensional data through the whole head, and what we've done here is we draw a line through the patient, right, so from their nose to the back of their head, and we ask the question, what is the maximum pixel along that line? And just display that. And so that is a form of projection of the data. You need 3D data to do it, but it's called a maximum intensity projection. It gives very stark contrast between the vessels in the background. And you don't pile up signal as you go through, right? So to do that, you need 3D data. Because those of you who are observant would look at this image and say, I could do this just with, an X-ray fluoroscope. I inject contrast in somebody's head, put X-rays through their head, and measure, the projection. And that it would look something like this. However, all of that data would pile up, and you would truly get a projection of all of the pixels through there. If you have three-dimensional data, you can essentially look at what is the brightest pixel on that angle of projection. And so let's look at this case here where this patient was on the patient table. We started the CT scan and rolled the patient through the scanner while the scan was on. So raw data was taken as the patient's moving through the scanner, so you can get data from right up here at their clavicle all the way down to their hips, right? And so that's a fairly long chunk, right, of patient. You've moved the patient through the scanner while you're doing that. And the great thing is if you're a surgeon and you're trying to figure out what you're going to do for this patient because they have this enormous aneurysm in their aorta. So this is their heart here. The contrast is in the left ventricle, and the contrast is also in their aorta. And you see the ascending aorta comes up here, the descending aorta comes down here, and this is about where their diaphragm is, and you can see this huge expanded aorta in this patient. Right? So it's completely dilated, and this is called an aneurysm. If it's left alone, they may just have a happy life, or they may not. It may split, right? And then you have this internal bleeding and the patient's demise very quickly. So usually they come in and they'll fix this. They'll put some kind of graft or some fake aorta in there that won't break. So for surgical planning, data like this, where you have full three-dimensional, high-resolution representation of the anatomy, is exceptionally useful, right? And this has led to the use of CT in many, many instances. Virtually 50% of people that come into a hospital probably get a CT scan, right? Because it's so fast and quick and the images are so beautiful. So here, if we look at the three-dimensional data through a patient's chest, these are CT images. This is called an axial plane through the patient's chest. An axial is if I'm lying on the table and I take a vertical plane and chop down that way, that's through here. So the chest wall is up here. This is the sternum. This is the heart. The spine is down here. These are lungs. Okay? And you see very bright signal here. That's the blood inside the left ventricular chamber, and this is immediately after the injection of that contrast agent, perhaps 10 heartbeats after the injection because it has to go through the lungs and come back and get into the heart. So you time that. But the great thing about three-dimensional data as opposed to just doing fluoroscopy where you're getting projections, the X-ray data, is that we can cut this three-dimensional volume into an infinite number of planes to take a look at things. So if we look at, say, so this is axial. So this blue line here is parallel to the floor. Okay? The patient's lying on a table. We're now cutting something parallel to the floor, and this is what it looks like. So now we can see the aorta coming up from the left ventricle and get a view of the aortic valve. This is right ventricle. Here's the patient's diaphragm. And so you get another view of that patient from a different orientation. If we cut this view along this line here, that's called a sagittal cut. And that's straight down the center of the patient like this, or shifted one side to the other, but vertically. And that looks like this over here. And so their patient's chest is now over here, their diaphragm is here, and it's like we're looking from their left arm through sideways, right? You can orient these planes however you wish, right? So you can tilt them to match the physiology you'd like to image or investigate. You can draw curved planes and paint the image pixels from that curved plane onto that, and so now you have a curved plane that you have an image on. So if you're tracking a vessel, say, that curves, you can track it all the way around. And so once you have this 3D data, you can slice it and dice it any way you want. It's very powerful. So this, well, we're going to have to restart PowerPoint. Sorry about that, because the movie is not running. And it's kind of essential to see the movie. Okay. Any questions so far while we're firing up Microsoft again? Yes?
So the 3D data you're talking about is like a 3D K-space with a bunch of bright points?
Oh, that's a good question. So the 3D data we're talking about here, the question is the 3D data points in K-space? And in fact, the 3D data here are points in space, X and Y and Z, right? K-space is the spatial frequency representation of these data. And in CT, we'll look at K-space on occasion, but for the most part, we can think about it just in space, okay? And the detector array that obtains this data is just like a camera, right? It's just a 800 by 256 camera. And boom, takes pictures and takes them at different angles. We'll take a look at that in a second. So the other way, instead of slicing and dicing, is just let's look at all of the data together as a 3D volume. And so this volume is rendered using whatever your favorite 3D rendering software is. You can use RenderMan, you can use whatever the vendor gives you. And so each voxel in space, if I have an XYZ coordinate, each voxel has a brightness, right? It's just a number. And that number is usually somewhere between -1,000 to 5,000 in CT for historical reasons. But it's a number. And so the relative brightness of those numbers can get mapped and you can make a rendering. So very bright things in this image are inside the vessels. Right? So all those things are vessels because the contrast agent is running in the vessels and it makes them brighter than the surrounding tissue. So we can kind of eliminate the surrounding tissue and just look at the vessels. Right? This data was obtained in a fraction of a heartbeat. All of this data. So we have 512 by 512 by 256 pixels here. That's a 3D volume, that many pixels. And all of that was obtained in about 160 milliseconds, right? That's where CT is now. And so that's why it's an extraordinary imaging technology. Right? You can get that kind of data density at that speed. And pretty well nothing else matches it. If you have something, I'd like to know, right? So you can look at that image like that. You can also take slabs through the 3D volume. Let's take a slab that's, say, about 2 centimeters thick. And we'll just cut it along a direction. And we'll cut out the data. So now we have a slab. And through that slab, we'll do a maximum intensity projection. So we're eliminating all of the interfering data above and below that slab. Inside that slab, we may have something like a coronary artery, that we want to see very detailed information. We don't want to see anything above it or below it. Just cut it out and do the projection. And you can see these fantastic angiograms that are obtained by doing that. Right? And so if you're looking for, say, coronary artery disease in a person and you want to quickly see if it's there, you pull this up and you know immediately whether or not that vessel is blocked or it's open or etc. So again, that is because it's three-dimensional data. So we can take a look at subsets of that data quite well. The other thing you can do is look at data temporally. Right? So we're going to take images, say, every 150 milliseconds. We'll take a picture. It's a three-dimensional volume. That picture is a 3D volume. and we'll just take one every 150 milliseconds, right? And then we'll play them back just as a movie. It's that easy. It's pretty trivial, right? And when you play them back as a movie, you can see natural phenomenon occurring like cardiac contraction, right? So this, the bright signal here, is the blood in the left ventricle, right? And so as the left ventricle squeezes down, the blood volume gets smaller, and you can see that occurring here. So you can see the cardiac function pushing that blood down to become a smaller volume. The contrast agent is filling in all of the interstices and everything on the ventricle and giving you a cast of that left ventricle, right? And so if there's an abnormality here, you would see it. It would be quite obvious. You can see the shape of the aorta, the aortic valve, the coronary vessels. This is the left atrial appendage. This is the spine. This is the descending aorta back here, and then this is the left atrium, right? And what's really cool is you can see the left atrium contracting. That occurs at the P wave on the QRS, and so you get a quick atrial contraction before the QRS. And here, you can see the left atrial appendage just shrinking down at that P wave, right? And this can give you, information about the function of the left atrium itself. So, that's just to, whet your appetite as to why you want to know any of this math, right? Because if you know this stuff, you can make those pictures, right? That's basically why it's good to know this stuff. And you can make pictures that you trust, because anybody can make pictures, but sometimes the pictures are full of artifacts, sometimes they're geometrically distorted, sometimes the signal to noise is crappy, so you want to make good pictures. And so all the engineers over the last 30 years have been working on CT technology to get to this point where you're making remarkably good pictures, right? And we'll see that the uptake of the use of CT has sort of exponentially grown, which is a cause for some concern, which we'll talk about briefly. Okay, so the simplest way to do CT scanning was the original way it was done, probably. And you have a single X-ray source, okay? So this is your X-ray source here, right? So we're going to have X-rays coming out of this thing, okay? The beam, the X-ray beam, can be formed such that it's a thin beam, and then down here, what we'll do is we'll detect the X-rays that are coming from the source, okay, with a detector, and we'll just count the number of photons that hit that detector. Simply count them, right? And so if the X-ray source is shooting X-rays through air, virtually all of the X-rays are going to get to the detector, right? Because air really doesn't attenuate X-rays very well at all. If, on the other hand, we pass this source along here such that, eventually there'll be a pathway that goes through the patient will actually attenuate X-rays along that pathway, right? And ideally, what fraction of the X-rays do you think we want to have the patient attenuate? Just to take a guess. Do you want it to attenuate 99%, 1%, what? 50%? 30%? Yeah, probably about half, right? Because you want the object you're imaging to essentially be translucent, right? But you don't want all of the damn X-rays to go through it, because then your contrast is just on a small fraction of the X-rays you've shot through there. And what is the downside of shooting X-rays into a person? So you say radiation. So can somebody expand on that? What happens when you get irradiated? Now you don't get, all this stuff. Okay. Ain't it fun? So if you get high energy photons, high energy X-rays coming into your body, and they get stopped by your body, well, what happened there? Energy got deposited in your body, right? Now remember in the lecture about X-rays, how you make them and how they get stopped? Well, one of the ways of stopping them is they come in, they Compton scatter, they can shoot electrons off of atoms. They cause a bit of a mess, right? So basically, chemically, you can do things like break chemical bonds. You can cause breaks in DNA, for example. And the DNA breaks are usually fixed right away because your DNA is breaking all the time. And so you have this mechanism by which it gets fixed all the time. If you didn't, we would all evolve into cancerous beings very quickly, right? So basically, you've got this repair mechanism always going. However, if you put too much radiation, then you swamp out this ability to make these corrections. You get permanent damage, and that usually winds up being a cancer, right? But those doses are very, very high. Like for that to occur, you need a lot of X-rays for that to happen. We're usually working down on doses that are low. But ideally, we want to use the doses that are just enough, right, to get, say, 50% of the X-rays stopped and then 50% detected. So we have a nice translucent object. We can go into more details about that stuff if you're interested. So anyway, we're going to take data at this position. We're going to move both the source and detector across the patient, and we'll look at how many X-rays are absorbed at each position along that line. And this is often called L. This line here is L in that direction. We then rotate the whole gizmo, right, and do it again at a different angle. So we're going to take a projection through the patient at a different angle. So we'll look at them from the top, then we'll look at them from the side. And we'll look at them in a whole bunch of angles in between. Okay. What's another way of doing that? Do I have to rotate the gizmo? I can rotate the patient, right? So, you know, when Jerry Prince and I were having a burger at PJ's in Baltimore, I said, look, you know, we should do 3D CT imaging just by putting stand a patient on a thing that rotates, stick them in front of a chest X-ray machine, and just spin them, right? So they just stand there like this, just go, zzzz, and you spin them. And he said, yeah, that's okay, but on a chest X-ray machine, the beam comes out as a cone, right? And so it's really hard to reconstruct. It's not going to be that useful. So it turns out to be very useful. But anyway, yeah, you can just rotate the patient, right? You just need a different angle, different view. And a way of speeding this up, that was the first generation of scanners, and that was done by, you know, Dr. Liu told you about Godfrey Hounsfield. He won the Nobel Prize for basically coming up with this whole ability to do this. And the first commercial machine actually did something like that. To speed it up, you could let the X-ray source, right, have some width, like a beam, like this, and then put multiple detectors down here. So instead of just detecting one spot, maybe I'll detect 8. And I can go 8 times as fast, like raster along, or maybe 64, etc. So that's the second generation. And then we get to pretty well where we are today, which is I'm going to put detectors all the way along so that I can image the entire field of view in one shot, right? Or a projection of that whole field of view just in one go. So if I go poof and take my X-rays, then I'll collect them here and I've got that projection. I don't have to raster the machine around. It's much faster. But normally what a CT scanner does is that this whole gizmo with the X-ray source and the detector usually rotates around the patient, right? And that rotation speed nowadays is usually about 280 milliseconds for one complete rotation. And so this, you know, the third generation scanner is kind of where it stopped. The other way of speeding things up, though, now that I have all of my detectors, along this way, say I have, 800 or 1,000 detectors along that way, when I look in the orthogonal direction, the slice direction, this is the Z direction, right? I could just stack these things up. So I could take multiple slices, 1, 2, 3, 4 slices along here. And now I've got I'm 4 times as fast, because I'm taking 4 slices simultaneously. Well, let's do 8, and 16, and 64, and 128, and 256, and now Toshiba does 320 slices in this direction. Right? So now you truly do have a 2D detector camera thing that is just taking essentially what you would get if you stood a patient in front of an X-ray machine, right? You get the whole field of view, right? And you can now obtain those images, enough data, such that you get all of the 3D information you need in about 160 milliseconds for one volume. So this is what the geometry looks like now with basically the detectors along the arc this way and in Z that way. When machines got to 64 slices, CT just took off in terms of usage because it became so fast to do a CT scan. Up to that point, to do multiple slices, we'll see, you had to sort of stop and take a whole bunch of slices, and an exam would take, 20, 30, 40 minutes, right, for a patient. Now an exam takes 4 minutes. Like you get them in, you go boop, and then off, next patient comes in, right? And so it becomes exceedingly cost effective, like because you can just do many, many patients in a short amount of time. So how do you acquire the volume data? So this is up in the top left here is the basic geometry of the CT system, in that we have our source here and our detector over here, and that whole object is going to spin. It's going to spin around the patient, and as it's spinning, for each angle, we'll take data. And so we'll do usually about 800 angles, something like that. Right? And we'll figure out why you want 800 angles. To move and get different slices, if this is a one-slice scanner, initially what happened was the table would shift, say, 2 millimeters, and you would do that whole thing again, and the table would shift another 2 millimeters, and you'd do that whole thing again, and you would just step your way through the patient, right, or the volume you wanted to scan. In the early days, data was streamed out of the detector on a ribbon cable, right? So you had preamps and stuff, you had the X-ray detectors giving flashes of light, and then basically that was turned into a voltage, and then you measured that voltage, and that came out on a ribbon cable into your signal processing device. The ribbon cable, obviously, if you go around the patient 360 degrees, well, it can't just keep twisting, right? So you would do 360 this way, then 360 that way, then 360 this way, then 360 that way. Because this cable had to go around and then come back, and it was all very sophisticated on how they had the cable set up. And then Siemens was the first vendor to introduce slip ring technology. And what this meant was all of the signals came out over brushes that essentially you had an electrical contact and a brush that, as the gantry was rotating, you had a continuous output of signal across these electrical brushes. So you didn't have to go backwards and forwards. You could just start the thing spinning and keep it spinning, right? So at that point, why not spin it fast, right? And so they did. They just kept cranking up the speed. And so these things used to spin sort of once every 2 seconds, in the days. Now it's almost 5 times a second this thing is going around. And we'll see a movie. That presents an engineering problem in that you have to design stuff that can put up with the g-forces associated with something spinning at 5 hertz. So 800 kilograms of stuff spinning at 5 hertz, which is why Siemens and GE and Toshiba, these heavy iron companies, make this stuff, right? It's like GE makes jet engines, which spin faster. They also make, washing machines. They spin pretty fast. So, so basically, once slip ring technology came along, right, you could just continuously move the patient. You didn't have to stop, take data, move the patient, go the other way. You could just roll the patient through continuously and take continuous data. And so now, instead of individual discrete slices of data, you had data that was kind of mixed. For a specific width on the patient, you had enough rotation to get data, but it was a little bit tilted, right? Because that patient was moving through. And then multi-detector, or MDCT, came in where you now have these multiple slices simultaneously acquired. You can still do the continuous motion of the patient through the scanner with multi-detector CT. You just get to move the patient a lot faster, right? So now, like on a Siemens scanner, I think the patient is moving through at about 70 centimeters a second or something. It's pretty fast. And so the whole thing just boop, happens really quickly. So here's a little movie of what a modern, this is a GE Revolution CT. They just take a video of the thing spinning, spins up to about that speed. It's covered so the patient doesn't see that happening, right? Because it's a little disconcerting when you're in there. And so here is the detector. Okay, this is the X-ray source up here, and this is the detector. And so the detector has enough length in this dimension such that if something is at the center of the scanner, we can cover 16 centimeters, okay, in the center here. And so that goes out to about 20 centimeters down here. And so there's, I think, 832 pixel elements in this dimension. So that's like the theta dimension, right? And there's 256 in the z dimension. So you're getting 256 slices of the patient simultaneously, right, as we're doing this imaging. This thing here generates a high voltage between the anode and the cathode in the X-ray tube. Okay, and you guys review back, think about X-ray generation. Remember, we needed a high voltage between the electrons burning off the cathode and hitting the anode. So this generates, up to 140 kilovolts, and it goes down to usually around 70 kilovolts is the lowest differential, because that's the range of X-ray energies that produce, or the range of electron energies that produce X-rays with the right energy spectrum to go through a person. If you use energies that are low, all of those X-rays get stopped, right? And all you get is an outline of the person. You don't see anything inside, right? If you use an energy that's too high, virtually all of the X-rays go through, and so you don't really see much contrast. And so you have to hit that sweet spot where the X-rays sort of get stopped on the order of 50%. This thing also is a very interesting design strategy of General Electric. Everybody takes their own path on this one. But what they've done is they've made an X-ray voltage generator here that can flicker between two energies. So it can go 70, 140, 70, 140, 70, 140 at a few kilohertz. And so this beam is sort of flickering between two energies, so you can take an image at one energy and an image at the other energy simultaneously, which is pretty cool. And we might look at why you'd want to do that. So this is what that system looks like when it's being installed. This was installed here in April, maybe 2 years ago, something like that. So it's a hefty piece of equipment. All of this gear here is rotating at 280 milliseconds per 360 degrees. It is spec'd, it's mechanically spec'd to rotate at 200 milliseconds. So 5 hertz, right? Except at that, the stuff up here is under 80 Gs, and this is the X-ray tube. And the X-ray tube they have right now doesn't work at 80 Gs, right? You've heard of microgravity? This is not microgravity. This is megagravity. And so that it sort of bends things out of shape, and so you need a new X-ray tube to get it to work at those high rates. So that's what we're waiting on. And if you want some entertainment, there's countless YouTube videos of engineers, little rascals, taking covers off and starting this machine up and then walking up with their camera and taking a picture. And so here's a couple of them here. And it's pretty impressive, right? The noise and everything this thing makes. So one of the engineering criteria for these new CT scanners was to try and get the noise down of this rotation, because it's a little disconcerting when you hear the thing, going faster and faster and the frequencies get higher and higher and the patient's in there going, what the heck? And you remember that EKG monitor? You can see their heart rate start to go up, right, as the noise goes up, and you're like, oh, no, calm down, everything's cool, right? So that is the Generation 7, I guess, CT scanner is what do we got? What time do we go till? 12:20, so we got 11 minutes, okay. With these multiple detectors along this arc, that's called the 7th generation scanner. 7.5 generation, this is a Siemens design, where you have a detector and an X-ray source, sort of a normal detector and X-ray source, slightly smaller. But then you have another one over here, right? So you've got two CT scanners sort of like imposed upon each other at a 90-degree angle, right? And so now you can get two simultaneous views, and we can go basically twice as fast, right? Because you really only need to rotate this thing just over 90 degrees to get all of the views you need for a picture, right? So now this thing gets you pictures in about 65 milliseconds, right? And the downside is that the detector itself on this design only has, I think, 96 slices as opposed to 256. So it's a bit shorter, probably due to the mechanics of having all this gear inside this gantry and rotating it. But at this YouTube site, they'll probably show you the whole thing rotating, etc. So that's a really cool way to make things faster, right? Is put two scanners in one. So here's sort of the history of CT or CT usage. Like when people go to a hospital, do they get a CT scan? That's a question here, right? So here's 1980. So CT was invented back here, 1970, say. So by 1980, you're doing about 2 million CTs a year in the US. Somewhere around there, right? It humps along like that. Helical CT, this is where that slip ring technology gets invented, right? And we start growing on a different slope, basically. The uptake of CT in different applications goes higher. Once we start putting multiple slices in there, people just can't, go without a CT because the images are so nice, and the usage just takes off, right? So now you've got 70 million CT scans a year, and this is in 2009, right? We're in 18. 70 million CT scans a year done, right? That's a lot, and like when you see the data, it's not a big surprise because it's super helpful. The question now is, you now have, say, 100 million people a year getting CT scans. How many people live here? 300 million? Wait a minute. You're irradiating a third of the population, right? So now you're in population numbers. And so people start getting concerned when you start doing things on population scales, right? And say, well, perhaps, like if we count up all of the radiation, it looks like half of the radiation in the whole population comes from CT scans, right? So living here, walking around, getting hit by cosmic rays, and radon is the biggest source of your exposure to radiation. You get about 3 millisieverts a year. You won't know what those units are, but let's just say it's 3 millisieverts a year. A CT scan can be anywhere from 1 to 15 millisieverts, right? Sort of in that area. So you can be around the baseline exposure, right? So if people are getting 5 millisievert scans and 100 million people are getting them, then the baseline radiation dose for the whole population goes up. Does it go up enough to change the amount of cancers that are discovered? That experiment is very hard to do because the rate of cancer is very high, right? 30% of people, get cancer. You live long enough, you'll get cancer, right? So if you're really healthy and you do really good cardiovascular care and keep yourself going, you're just going to die from cancer. So, but that's old when you're old, right? If you just last long enough, you will have mutations to generate a cancer, right? So the question is whether or not this actually increases your odds of getting cancer or not is a still open question, right? Because it's such a low dose that the experiment is terrifically hard to do, right? You could not measure the change in the rate of cancer at these doses unless you had like 6 billion people in the study, right? But anyway, it's some concern. So here's a chart. You don't really need to know the details of this chart because we're pretty well going to concentrate our stuff down here at the 7th generation. But the 1st generation scanner is interesting to know because most of the math on how you reconstruct CT from projections still goes back to that 1st generation scanner. We still make these assumptions like we're going to have parallel beams, of X-rays come through. And if we collect them in some other way, usually the data is resorted to try and put them back into these parallel beams, right? And so it's worth sort of knowing the principle there. So what does a detector look like? This is a panel, one of, I guess, about 12 or 13 panels of detectors, X-ray detectors in that GE scanner. So these are the elements that actually flash when an X-ray hits them. So it gives off a fluorescent flash, and then it's changed to a voltage. That goes down to a preamp. This structure up here is an anti-scatter grid. You would like to detect X-rays that are coming straight from the source and missing the patient, right, and hitting your detector. You don't really want to detect, on this part of the detector, you don't really want to detect an X-ray that goes here, bends, and then comes back this way. That's called scatter. And it doesn't enhance your image. It just puts cloud on the raw data, right, of just a fuzz. And it's kind of like shining a light through your hand. You can see through your hand, but it's very blurry, right? It's just this red blurry thing because all of the light is being scattered so much, right? So actually we can, since we have, how many minutes left? We got 4 minutes left. Oh, this is a little movie of what, if you're looking through the anti-scatter grid, as you change your angle, you can see that certain things come and go depending on what angle you're looking at. So these are the objects under the scatter grid, right? So the purpose is basically just to keep X-rays on a straight line that you're detecting. Get rid of the scatter. I'm going to hop into one thing over here I brought up. Yeah, this thing's pretty cool. So this shows it blows up the detector. So it's compartmentalized into these units. This is the Z direction. Okay, so this is the slice direction, right? And multiple detectors like this are stacked parallel to go in the theta direction. And then inside each one of these, so we have this anti-scatter grid above. This gives us our 160 millimeter coverage in Z. And then these little chiclet guys have, I think it's 16 by 32 detector elements on them. Right? So it's just a digital camera for X-rays. It's just like your digital camera in your phone is, nowadays they're like 2K by 3K or something like this. This thing is 832 by 256, right? But it's a very special digital camera. It's an X-ray digital camera. And so that whole thing is stacked together. and then we bring it back into place here. And so there's, I think, 832 by 256 detectors on there. And hopefully, if you turn on your X-ray source and you irradiate that area on your detector, you would hope that you would see a very uniform illumination if there's nothing in the scanner, right? You're scanning air, so you would hope that it's a uniform illumination. It is not, right? There are reasons why it's brighter in certain places. Electronics, the amplification is slightly different in different places. The X-ray source changes a little bit over time as you're doing a scan. So all of those things have to be thrown into a correction. So everything's sort of self-normalized usually in a CT scanner so that you get relative amounts of X-ray attenuation at each one of these detectors. Okay, so that's an introduction to the technology and to some of the images. When we come back on Wednesday, we'll go back to the math and we'll look at how do you write down the equations for the attenuation of X-rays in front of this detector, and then how to use that data to make the CT scan. So any questions before we depart in the back? Yeah? It does both. So if you have the X-rays on for a shorter time, you can imagine your dose would go down. However, there's a certain number of X-rays you need to get images of a certain signal to noise. Whether I get them over, 200 milliseconds or 100, I still need to get them, right? So that is kind of fixed in terms of a dose. So the reason you want to go fast is to try and freeze motion. Any other questions? All right, great. See you on Wednesday.